Okay. Good afternoon. Kailas sir, whether I am audible? Please give reply in chat box. Hello. Kailas sir, whether I am audible? Audible or not? Okay. Good afternoon. Today we will see digital transducers. Already we have seen one type of transducer in earlier lecture, but still we will continue. I will repeat it. The transducers described so far are analog ones. That is, their output varies continuously according to the input. In digital transducers, however, the output is discrete and may give frequency type output or a digitally coded output of binary or some other type. The main advantages of digital transducers are: first, use of digital computers along with the transducers for data manipulation is made easier. Digital signals, pulse count frequency or sequences of digitally codes outputs are not dependent on signal amplitudes and are thus easy to transmit without distortion and external noise. Increased accuracy in pulse count is possible. There are ergonomic advantages in presenting digital data. Digital transducers range from frequency domain or frequency generating types of transducers to digital encoders. Alternatively, an instrument may incorporate an analog transducer and an analog to digital converter, giving a digital output. Figure 3.29 shows such an arrangement. Therefore, digital instrument incorporating analog to digital converter. In that first, this block diagram is there. Physical variable, whatever that pressure, temperature, force, whatever these different physical variables are there, displacement. That physical variable is given that input to the analog transducers. Then we are getting analog signal. Then analog to digital converter is there. From analog to digital converter, it converts analog signal into digital signal, and we are getting digital output signal. Now, in that first is the frequency domain transducers. In these transducers, the output is in the form of pulses or sinusoidal waveforms, the frequency of which is a measure of the magnitude of the physical variable. Frequency can be measured by a frequency or pulse counter. Three types of frequency domain transducers have been described below, with electromagnetic frequency domain transducers, optoelectrical frequency domain transducer, and vibrating string transducer. First is electromagnetic frequency domain transducer. This type of transducer can be used for speed measurement as shown in the figure. The device consists of a permanent magnet or a solenoid on the rotating shaft whose speed is to be measured. A gear of ferromagnetic material is attached. As each gear tooth passes in front of the magnet, the gap length changes. This changes the flux density and a voltage pulse is induced in the coil. Pulse frequency equals speed n times the number of teeth, capital T. The form of the output signal is also shown in figure 3.30. Thus, pulse frequency is a measure of speed of rotation. Therefore, the shaft whose speed is to be measured, we are going to mount a gear of ferromagnetic material on that shaft. This is the magnet. Now, what is happening when this shaft will rotate or in turn gear will rotate? Because of teeth on the gear, there will be change in the gap between the gear teeth or whatever that bottom land is there, top land and bottom land of the gear teeth. Therefore, because of top land and bottom land, that distance every time that distance between magnet and gear teeth will change, and depending upon that, that output signal we are getting or flux density will change, and these changes in the flux density, what it will happen, a voltage pulse is induced in the coil, and this pulse means frequency. Therefore, this pulse frequency equals speed n times the rotation of t. The form, therefore, we are getting whatever the signal form is there, that is nothing but digital form. Next is optoelectrical frequency domain transducer. Figure 3.31 shows an optoelectrical frequency domain transducer for the measurement of speed of rotation of a shaft. The shaft has half dark and half white or shining portions. This is the shaft, this is half dark and half white. Every time the latter portion is in front of the light source, that is latter portion means that shining portion. The reflected light falling on the photoelectric transducer gives an electrical pulse output. The frequency of the pulses is thus a measure of the speed of rotation. Therefore, whenever this shaft will rotate and this light will fall on this shining surface or that white surface on the shaft, therefore that light will get reflected and it will be catched by this photoelectric transducer. From the photoelectric transducer, we are getting output signal and it is fed back to the counter. Therefore, for measurement of linear motion, an arrangement using the optoelectrical device is shown in figure 3.32. This is for rotational movement. This is for linear movement. This uses a transparent scale. See that this is the transparent scale with grating. With a grating, the moving object is attached to the transparent scale. The moving object is attached to the transparent scale. Light from a source passes through the scale. Therefore, when this light will pass through the source, through this lens, to this scale, and a slit. This scale is having small apertures or small gaps that are known as slits, and then falls on a photoelectric transducer. This is the photoelectric transducer. This is the slit. The slit width is such that a motion equal to the pitch of the line grating produces one complete cycle of light and darkness at the photoelectric cell. Thus, a pulse output is obtained from the number of output pulses. The change in motion of the scale and the object attached to it can be determined. Next is the vibrating string transducer. This is essentially used to measure the force applied to a metal string which is kept vibrating, the frequency of which is dependent on the force applied. The natural frequency F of a string of length L and area of cross section A is given by F is equal to 1 upon 2L into square root of P upon A into rho, where P is the force applied and rho is the mass density of the wire material. The arrangement is shown in figure 3.33. One end of the string is fixed and other end can be moved relative to it due to the force applied. An electromagnetic transducer picks up the vibrations. Therefore, when this force will be applied at the other end, this string is going to vibrate with small amplitude, or this vibration generator is there. Because of this vibration generator, it is also known as exciter. The spring is going to vibrate. An electromagnetic transducer picks up the vibrations, the output of which after amplification is fed to an electromagnetic vibration generator, which maintains the string vibration at its natural frequency F. Frequency of gets changed due to change in magnitude of force P. The frequency is measured by a frequency counter and is a measure of the force applied on the string. Initial string vibrations are obtained by an electromagnetic device that plugs the wire on application of a pulse. The transducer can be used for force and displacement measurements. Next is digital encoders. These convert analog motion, that is rotary or linear, directly to a digital output form. Figure shows a rotary encoder disc. This is the rotary encoder disc. See that it is having number of circles, and whatever that circles are divided into these light and dark portions by using different sector or by using different angles. A, B, C, D, E. Means one disc is there, and in that they have made 5 parts. The encoder disc has 4 bits or tracks and is divided into conducting or insulating portions. Brushes A, B, C, and D are stationary. Brush E being on the common energizing track, which is a conductor. When any of the brushes A, B, C, or D is on the conducting portion during rotary motion of the disc, the circuit is made and corresponding indicator A, B, C, or D is on. Otherwise, it is off. That is state 0. On means state 1. The outermost track corresponds to the LSB track, and the innermost to MSB track as shown in the figure. Figure also shows the natural binary numbers with their decimal equivalents in brackets corresponding to various possible brush positions during the rotational motion of the disc. The disc shown has a resolution of 1115. With increased number of tracks and brushes, the resolution can be reduced. The information can be supplied directly to the computer input switches in binary digital form. In a similar way, an encoder can also be used for linear motion input. The encoder described above uses natural binary code. It can be seen that the motion from one position to the other may require a change in the number of brushes for conducting to non-conducting surface or vice versa. If due to any misalignment during the change from one position to the other, all brushes do not change simultaneously as required, an error can occur in indication. This is overcome by using a different type of code. The arrangement described above is of contact type, as there is direct contact between the brushes and encoder disc. The disadvantages of such systems are wear of brushes and disc and friction between the brush and disc. Some other types of arrangements are based on a different principle. These are of optical and magnetic types. But this is the disc. If you see, this is the common energizing track. This portion with the hatched lines shows conductor, and the portion which is not hatched, it is known as insulator. An optical type encoder is shown in figure. See that this is the encoder disc, lamp, convex lens. Then that rays goes, light rays, and it will pass through the encoder disc. It will move through the slit and it will fall on the photocells. The disc has transparent and opaque areas corresponding to the conducting and non-conducting ones respectively in the contacting type encoder disc. A light source is used along with slits and photocells. The photocell corresponding to a particular track would produce an electrical output if the transparent portion is in front of the slit and light source, giving state on or 1, while no electrical output from a cell would correspond to off or 0 state. The magnetic type encoder is also of non-contact type. This uses a number of small toroidal magnets with coils around them. The area corresponding to the conducting and non-conducting ones in the contact type encoder disk form the non-magnetic and magnetic areas on the disk. The presence or absence of such areas is detected by the coils which are in close proximity to each track on the disk. One of the coils in each toroidal magnet is energized with high frequency AC carrier signal. If the toroid is over a non-magnetic area of the encoder disk, a voltage due to transformer action is induced in the output coils. That is state 1. While magnetic area would saturate the magnetic circuit and output is small, state 0. The signal on the output windings are usually demodulated to remove the high frequency carrier signal. Next is intermediate elements. Now all these whatever we have seen, it is all aware transducer elements. Now intermediate elements means what? Filters, analog to digital or digital to analog converters, amplifiers. Therefore, intermediate elements. Introduction. The output signal of any transducer usually needs to be modified by elements known as intermediate elements so that it can be displayed or recorded with convenience as desired. These include first amplifiers for amplifying the transducer output, which may be small, compensating devices in order to improve characteristics like frequency response, impedance loading, etc. Differentiating or integrating elements so that the output is proportional to the desired input, which may be, for example, displacement, velocity, or acceleration in any given situation. Filters for filtering out unwanted positions of the signal. Analog to digital or digital to analog converters for converting analog type signals to digital form or vice versa. Data transmission elements which transmit the transducer output to a certain distance as desired, for example, from a running machine in an inaccessible location to a control room. Amplifiers. Now, first of all, we'll say amplifiers. Amplifiers are intermediate elements that increase the magnitude of the signal from a transducer so that it can be conveniently displayed or recorded. These may be of mechanical, hydraulic, pneumatic, optical, or electrical or electronics types, depending on the type of transducer. In cases where a reduction is needed in the magnitude of the sign of the signal from the transducers, these are called attenuators. Therefore, first of all, Amplifiers. Amplifiers are intermediate elements that increase the magnitude of the signal from a transducer so that it can be conveniently displayed or recorded. These may be of mechanical, hydraulic, pneumatic, optical, electrical, or electronic types, depending on the type of transducer. In cases where a reduction is needed in the magnitude of the signal from the transducer, these are called attenuators. Now, first is the mechanical amplifying element. Mechanical amplifying elements are simple in operation, rugged type, and inexpensive. They find a wide range of applications in the mechanical type instruments. For example, Hugenberger extensometer employs mechanical amplification using a system of compound levers. A dial gauge with a least count of 1 micrometer employs a system of gears to amplify the displacement input. Further, a board-on pressure gauge employs a combination of levers and gears to give the desired amplification to the transduced displacement signal. However, these types of amplifiers have the advantages of friction and friction effects, backlash errors, and inertial effects due to relatively higher mass. They are also affected by environmental temperature changes. Figure 3.37 shows a lever mechanism that is a typical mechanical amplifier. As seen from the figure, the output signal X naught is given by X naught is equal to R into Xin divided by small r. Therefore, this lever or mechanical amplifier is divided into two dimensions, capital R and small r. For small displacement here, we are getting large output. That's why it is known as amplifying element. Similarly, for angular motion using gears for mechanical amplification, the output signal theta naught is given by theta naught is equal to n into theta in divided by small n, where capital N divided by small n is the gear ratio. Next is the hydraulic amplifying element. Hydraulic amplifying elements find a wide range of applications in the form of hydraulic actuators in the control elements used in the automobile, hydraulic brakes, and hydraulic steering systems. The advantages is compactness for a specified force, while the disadvantages are possible leakages and problems in dusty environments. Figure shows a typical hydraulic type element in which the output signal X naught is given by X naught is equal to capital D divided by small d bracket square into Xin, where capital D and small d being the respective diameters of the plunger and pipe respectively. This is the plunger, its diameter is capital D, this is the pipe, its diameter is small d. Pneumatic amplifying element. In order to amplify pressure signal P2, here this P2 pressure signal, a ball type relay is shown which this is the ball type relay, which is operated by the motion of an elastic diaphragm. This is the elastic diaphragm, which gets deflected to P2. If the ball is at their lowest position, pressure P3 is atmospheric pressure. See that this P3 pressure is atmospheric pressure. While at the topmost position, P3 equals air pressure P1. At topmost position, this pressure P3 is equal to pressure P1, that is atmospheric pressure. Thus, P3 changes from zero gauge pressure to P1 due to small pressure change in P2, and so the relay can be treated as a pneumatic amplifier. I will explain the working. These are used in industrial environment where compressed air is easily available. Now you just see, this is one pipe or tube is there. At the end, it is having nozzle shape. Now, this is the flapper. This flapper, you can move either towards left or either towards right. Now, if this, because of this flapper, this back pressure is getting generated. Now, if the air supply is there, what will happen? Air supply will be at pressure P1. Now this air will go through this aperture, it will move and it will come out through the nozzle. Now if this flapper is there, if we'll adjust its distance from the end of the nozzle towards right or towards left, therefore what will happen? If it will go towards left, what will happen? There will be resistance to flow of the air outside the nozzle mouth. Therefore, because of what will happen, here back pressure is getting created. When back pressure is created, what will happen? This ball will come in the downward direction. This ball will come in the downward direction. When this ball will be at lowest position, what will happen? Pressure P3 is the atmospheric pressure, while at the topmost position pressure P3 equals the supply pressure P1. Thus P3 changes from 0 gauge pressure to P1 due to small pressure change in P2. Therefore, this is pneumatic amplifying element. Next is optical amplifying element. One common application of the optical amplifying element is in the taut suspensions type of the optical type galvanometer, which is a very sensitive type of instrument. The lamp and scale type of amplifier is relatively inexpensive and provides a large amount of amplification to the input signals. However, these amplifiers, because of their inertia effects due to mirror mass control, mirror mass cannot be employed in the dynamic type of measurements. In order to amplify the angular displacement, that is theta I, as shown in figure 3.40, an optical arrangement is used. Therefore, you just see this is the concave lens. Now, when this light ray will fall on this lens, what will happen? This small lens will get deflected, and therefore, because of deflection, what will happen? This light ray, that light ray reflected from this small lens, it will move towards like this, that is towards right upper corner, and it will strike on this scale. Therefore, this small change in input, we are getting large change in output. This means amplification is there, amplification of signal. Now next is filters. Filters are meant to remove unwanted signals from the desired transducer signal so as not to obscure the effect of the latter. Depending on the application, filters can be mechanical, electrical, pneumatic, or hydraulic. Figure 3.41 shows a typical mechanical filter. The reference junction of a thermocouple is kept in ice contained in a thermos flask, the insulation of which protects the system from ambient temperature changes. Similarly, in figure 3.42, a delicate instrument is shown mounted on vibration isolators to isolate the instrument from disturbing vibration inputs. Therefore, this is the typical mechanical filter provided in the thermocouple device. See that this is the box, it contains ice. This is the thermal insulation, this is the reference junction. Similarly, we can use this spring mass and damper arrangement to isolate the vibrations so that minimum amount of vibrations can be transferred to the machine or transferred to the instrument, so that accuracy of the machine or accuracy of the instrument will not lose, or it will not get deflected. Accuracy means accuracy and precision, both things we require for the instrument as well as for the different machines. Precision indicates repeatability of an instrument to produce given set of readings every time. Now classification of filters. In general, filters are classified as shown in figure. The amplitude ratio of output of the filter to the input is plotted against frequency. The low pass filter figure 3.43a will pass signals of low frequency till frequency of 1. The high pass filter figure 3.43b will pass signals from frequency h onwards, while the band pass filter will only pass signals which lie between frequencies f3 and f4. See that this is a band pass filter. The notch type of filter figure 3.43d will block all signals that have frequencies between f5 and f6, while all others will appear in the output. Figure 5.24 shows the ideal filter characteristics, while in actual filters, the output to input amplitude ratio does not vary sharply. Figure 3.44 shows a low pass filter, electrical filter, for which the ratio of output to input voltage is given by E2 upon E1 is equal to 1 divided by 1 plus tau d, where tau is equal to RC. The frequency response of the above filter is similar to the plot in figure 3.43 with the sharpness of cutoff depending on the value of t. In figure 3.45, a low pass filter has been used with 3 resistance strain gauge bridge for filtering the unwanted noise signals of high frequency. The low pass pneumatic filter may shown in figure 3.46. If m is the mass flow rate and mass flow rate through the restriction with fluid appearance or with fluid appearance, now figure 3.45 shows a low pass filter has been used with 3 resistance strain gauges. See that this is the resistance strain gauge 3, 1, 2 and 3. Bridge for filtering the unwanted signal or noise signals of high frequency. The low pass filter pneumatic filter shown in figure 3.46. This is low pass pneumatic filter, that is it will pass if m is the mass flow rate through the restriction with resistance flow rate with fluid resistance R showing to a type showing to a the low pass pneumatic filter shown in figure 3.46. If m is the mass flow rate through the restriction with fluid resistance R flowing to a space of pneumatic capacitance C, then according to the definitions of R and C, P1 minus P2 divided by R is equal to M is equal to CD into P2. P2 divided by P1 is equal to 1 divided by 1 plus tau D, where R is equal to small r is equal to RC. With such a filter, high frequency pulsations can be removed from the pressure signal PI Figure 3.47 shows a simple high pass filter which can be shown to have the output signal. Therefore, here input upon output, it upon E1 is equal to tau d divided by 1 plus tau d, where tau is equal to RC. The use of low pass filter along with high pass filter will result in a band pass filter. Similarly, the filter shown in figure 3.48 can be shown to have characteristics of a notch type filter corresponding to the characteristics. Now next point is analog to digital converters and digital to analog converters. Okay, the simplest form of an A to D converter is of potentiometric type and is shown in figure 5.30. This employs comparison elements that are in the form of semiconductor relays or magnetic cores. These elements change their state on or off if the input signal is greater than or less than a fraction of the reference voltage to which they are connected. The potentiometer resistance are weighted so that the reference potentials are according to binary values 1, 2, 4, 8, etc. An automatic switching unit compares the analog input value with the reference voltages starting with the highest, and the comparison elements change their state accordingly. Now this is the potentiometric analog to digital converter. See that? Now based on a similar principle, a successive approximation type analog to digital converter employing digital to analog converter is commonly used as shown in figure. See that this is the comparator, this is digital to analog converter. We are getting 4 different signals. In the above converter, the analog input from a sensor is compared with the voltage generated by a digital to analog converter from a logic and multiple bit storage register successively in a certain sequence. When the two are equal, the convention is ended with an acceptable digital output is available. The sequence usually employed consists of selecting the MSB that is available in the analog value, then adding successively the less significant bits for which the total does not exceed the analog input, that is 4 bits are used. We may start with 1000 and by the logic shown here, that is 5.1. In table 5.1, we get the acceptable values corresponding to various cases involving different values of analog signals. In a similar way, the trails for other analog values in the signal 0 to 15 kilometer 0 to 15 can be written if the number of bits in the range 0.255 to 0.255 0 to 0.02255 can be obtained by trial. In this method, an n bit word takes n steps for comparison, and time taken to obtain the bit word is n divided by f, where f is the clock frequency. Sorry, f is the clock frequency. Another analog to digital converter is based on a different principle. This is called counting type analog to digital converter as shown in figure 3.52. This is counting type. As shown in figure, here the analog input voltage EI is compared against a ramp voltage ER. generated by a ramp generator as shown in figure 3.53. The time taken to reach equal values is a measure of the analog input voltage EI. Since the slope of the ramp voltage is constant, in order to get a digital output proportional to the time taken for the two voltages to be equal, which in turn is proportional to EI, an electronic gate is opened to permit the output from a frequency oscillator to be fed to the counter. The gate is open for the times T1, T2, T3, etc. Besides, since the frequency of the oscillator is constant, the number of oscillations counted by the counter is thus a digital measure of the analog input voltage EI. The counter can be arranged to give a binary output if required. The opening of gate according to the beginning of ramp and closing of the date when EI is to be are controlled as shown in figure 3.52. Now digital to analog converter. Okay, this last we'll see and then we'll stop. Now we'll see digital to analog converter. When the measured variables have to be transmitted, when the digital signals have to be converted to analog ones, the switching defining the digital signal value has to be changed to an equivalent voltage. Figure 3.54 shows one type of digital to analog converter similar to the potentiometric analog to digital converter discussed earlier. The switches are opened when a particular digital value is present. Otherwise, these are closed. Thus, the feedback resistance of the amplifier shown at any instant is the sum of the resistance values that are not sorted out. If the resistance in the feedback signals or feedback circuit are binary weighted with resistance values, say 2 degree, 2 inch, 2 raised to 2, 2 raised to 3, or 2 raised to 0, 2 raised to 1, 2 raised to 3, 2 raised to 2. And if a digital output, if the digital input of value 7 is present, the switches for digits 2 raised to 0, 2 raised to 1, 2 raised to 2 would be open, giving E naught is equal to minus of ER into 2 raised to 0 into plus 2 raised to 1 plus 2 raised to 2, which divided by capital RR, which is equal to minus 7 small e divided by capital RR. The analog output voltage would vary steps, but is smoothed out by filtering. Therefore, now we'll stop here. In next lecture, I will convert data transmission elements. We'll stop here. Thank you very much.